Yes, yep.
Okay, yeah, let's go with it here. So just real quick here for Taya. I'm going to give you guys a study guide soon. Next week, I'll give you guys the exam. And so we'll have like about a week to take the exam. We are going to take in outside of class exams for the rest of the time to get through this. But we do have to go about a section a day. We're good when we meet. Fridays are still going to be homework times to come in and do homework. I will also give you guys the homework for 310. Is that right? 310 is the last one I did?
You already did.
Okay, which one did I not give you guys?
I thought we had all.
Wait,
We have
310?
4, 7.
Oh, I did give you 310, 3 set. Yeah, I did give you 310, right?
We have all of it.
We didn't
About
do
4.8.
310.
Oh no, the solution set to it. They give you guys a solution set to
Oh,
310.
I don't know about that.
I don't know.
Okay,
I don't think so.
I'll send those to you guys just so you guys have them. But Fridays will be homework days, kind of if you need them. And I know we're going to be slightly tight schedule, so if there's something that's really bugging you, I don't mind sending you guys a worked out issue or just this. I'll keep on giving you guys a solution set, so at least you have that on top of that. Okay, does that works?
Yeah.
Okay, let's jam. So we have stopped doing derivative calculus, and we're going to go something called the integral calculus. Super cool stuff. We're going to jam through this here. We do have 32 slides, so about 2 slides a minute. We got to keep on going, but we'll skip through a few things already here. Good. So integral calculus, that's what it's called. Think about it going the other way. That's what it is, and some awesome, neat stuff come out of it. Okay, so chapter 5 is called integrals, just an intro. And then chapter 6 is applications of integrals. That's kind of where we're at. So 5.1, we're going to look at areas. What does areas have to do with this? We'll see. But let's go back to geometry here. Maybe some things I'll have you guys write down, some others I won't, just so we can kind of go through this process here. So from geometry, areas, talk to me. What area, we did that in, what areas do we know from geometry class?
Triangle, rectangle,
That's about it, right?
Rectangle.
Yep, rectangle,
Maybe
triangle,
triangle.
square.
I mean, in
Square,
algebra
yeah.
2, we learned
Wait,
like
we know rhombuses,
Quadrilateral.
Yes, correct. Quadrilaterals, parallelograms.
Yeah.
Let's see what else. Trapezoids, remember trapezoids?
Trapezoids are their own thing.
Oh, yeah, I
How
like
do you
Yeah.
use that?
I mean, they're still a quadrilateral.
You can break it up into different.
Oh, well, we did that by splitting them into 2 triangles and a rectangle. That's what we did.
Yeah.
And then we just found the area of the
Or
side.
even
It's-
3 triangles.
Yeah, you can think of it as almost like this is kind of cool because it is a triangle, right? But it's missing the top
Triangle
layer.
and the poke it off.
Yeah, so it's actually a plus b. You add the a and the b together times the height divided by 2. Technically, for a triangle, the a value is 0 and the b value is the base. So it's kind of cool. Circles, yes. And then n-gons. Remember n-gons? Like octagon.
Yeah.
That's what
Oh, I
Oh.
hated those.
And then the way the Greeks used to do them. I'm not sure if you guys did them like that. Yep.
Yep, that's how we did them.
Cool. Okay. And then something called diamond shapes or kites.
Just the
There's that as well.
Those are just, yeah,
Just a rhombus.
it's just.
Or rhombus. Yeah.
It's just a rhombus.
So they were they're distinguished from a parallelogram because they have?
No, they're just rhombus.
They're the same.
It's just a parallelogram.
Yeah.
It wasn't anything
Okay.
different. It was
All right.
the same.
So then we got this blah.
We did not do that.
We did not do that one. In fact, you can do that. That's our problem. Except for the fact that in real life, in order to get volume, like a Coke bottle, does a Coke bottle fit any of the things from geometry? Not exactly. It has a little curve shape, right? And it kind of goes in like this, right? And then it has a little top to it, right? It's very flowy.
You get close, but you can.
So that's what integral calculus is all about. How do I get that shape and actually get the area that's actually sitting there? But before we get there, dun, 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 am I recording? Yes. Okay. Before we get there, we got to think about something called some notation stuff. So let me write this out for you. I got A and B. Oh, yeah. Let me write this out for you. Let me write the top. So how about this? Write the sum in expanded form.
You know what order it's gonna go in?
This will be fun. We'll see. Write the sum in expanded form. So first things first, this guy is called sigma notation. That little funky looking thing is the capital letter for S in the Greek. So it's a capital S. There you go, Sadie. That'd be awesome.
Oh, I don't remember this.
That's why we're doing it.
We did that in algebra too, didn't we?
I don't remember this.
Yeah, we did. We also
That's-
did a bit of this in statistics.
Exactly.
Oh, cool, okay.
I don't remember
Okay, then it'll be a quick
Yeah.
review then.
We did.
We did.
I mean, we didn't write it out, but we used these.
We used
Uh-huh.
Theta.
It's
Theta?
Sigma.
That's not theta.
It's not
We
theta.
used Sigma.
I just
Chris
not
Mark.
remember that at all.
Uh-huh. So let's go talk about it first here. So I got this little guy here. Oh, look at this, an A and B. Look at that, I can put A and B. They'll come out funky little stuff. Okay,
Wait,
there.
what? Oh, okay.
there's example one, but then it's A and B. So sigma notation means you were going to be adding stuff together. That little I is called the index. You can choose any letter you like. And then we have a counter. Our counter starts at 1 and it goes up to 6. So we start here and we stop when it gets to here. Okay, tell me if you guys remember that from algebra 2? Okay, vaguely, okay. Some says no way. Okay, so let's go with it. So what we're gonna do is we're gonna plug in I is equal to 1. That comes in as 1. And we're gonna add, so plus. Then the counter goes up by 1. So
One, two.
2, thank you.
Wait, so it's just 6 factorial?
No,
No,
fact-
multiplication.
Six factorial is I.
Oh.
Would it be 6 factorial if it was addition? kind of?
we're gonna figure out the formula for addition. We're gonna have to figure that one out. Okay, and then that's it, guys. That's it. So we
N plus 1 plus 1.
21.
Yeah, that's what I got.
21. Okay. Awesome. You guys get the next one. Go.
4 plus 9 plus 16.
Only
Just
going
to
from
9.
three to nine.
What?
Just to
Three.
14.
Oh, 3.
Your handwriting is so tiny.
Yep.
I got 91.
91? What?
No, no,
I
it's only
got
to three.
14.
Oh, we only had 3.
Yeah, I made the mistake too.
This guy.
This guy, what kind of idiot would mistake that for the same problem?
Okay, are we good there?
Yeah.
Awesome. Okay, let's keep on going. C does like this, a little bit more complicated, not by
Is
much.
that a 6?
That's a 6. Uh-huh. So now we go from I is equal to 5 to I is equal to 6.
Wait, isn't that just, oh, 4 squared. Oh.
No, that's 4.
4 to the I, and you, so you do 4 to the
Ah,
Would that be, would that
see.
be 4 to the 5th plus 4 to the 6th, or do you put in?
I think it's 4 to the 5th
Ah.
plus 4 to the 6th.
So if
Because we
you
start
need,
with 1 on.
here's the thing, if you need the numerical value for it, then we'll do that. If you don't, then we kind of write it as an expression. In this case, for C, we probably should just get the numerical value for it.
Yeah.
For D, there's no way to do that because now we got some variables in there. And so with this one, 4 to the 5th plus 4 to the 6th, and let's do that. Since we have a calculator, we can probably do that real quick here. What is 4 to the 5th?
1024.
1024. 4 to the 6th would be then 4,096. Is it 96?
Yeah.
Oh, yes, okay. Sorry, I was multiplying by 2.
1,100 and 20.
Okay, everybody agree there?
I think.
I thought 120. Yeah. I thought 120.
Or 0.
Wait,
Yeah, by 120.
wait.
120.
Wait, yeah.
This guy.
This guy. Every time.
I'm great at reading the prompt.
Are we good there?
X to the 22nd, X to the 23rd, X to the 24th.
No, so you got,
What did
so,
you just do?
No, you don't add.
It's a multiplication.
Yeah,
Did you just do 20?
you just put the 2, 2
pages.
instead of doing 4.
Ah,
You turn it into 22 instead of just doing 2 times.
Gotcha. Yeah.
Oh.
Multiplication,
Yeah.
no problem. So I changed my index to K, which is perfectly fine. That could, usually they use I, J, or K. We use those three, and the normal one. Uh-huh. So x to the fourth, x to the sixth, is that right? And x to the eighth, and we gotta leave that as just an expression by itself. No way to do that. Boom, okay. There's that one. And again, tell me if I'm going too fast, because I'm hoping to get through this here. Okay.
Faster.
Okay, we're good?
Yeah.
Okay, let's go the other way. Example 2, exercise 2. Oh, hold on.
Oh, so you can get an expression.
Of course, hold on. Let me do one more. Let me do a fraction.
JK. Got him, 10 users.
Does that say N at the top?
N.
Yeah, we use
Uh-huh.
N sometimes as well.
Craziness. So talk about not getting the answer. Oh,
So you
man.
N plus 1 or something.
So I guess we start off, yeah. What would the first one be? 3/4, okay. 3/4.
And then can't you just go up and then you dot, like, dot.
4/5, 5/6. At that point, you could put a plus sign, you put just dot, dot, dot. And then at that point, you got yourself n plus 1 would be the value.
Now we have to look at
That's cool. So it's sometimes you just can't get to the right answer. We write out the expression itself. Sometimes the expression could be set. Sometimes in this one, it just goes on forever, right? There's infinite values here. Okay, let's go the other way. And so how about example number 2? So write the sum and sigma notation. So let's go backwards just to get us used to this here. So A is this right here, should be pretty easy. And B is, of course, I'm gonna put fractions inside here. It'll just be fun for fractions.
And so much easier the other way.
Yes.
Oh, yeah, I remember doing this because sometimes, what do we have to do? I can't quite remember what we did in algebra 2 with these things. We had to try to solve them backwards. And then we had to put it into something else. Another, I can't remember. Sometimes it got tricky and then you had to try to figure out what the sum was.
Mm-hmm.
Just trying to figure out what was happening.
Gotcha.
1/4. Oh, right.
Cool, so I'm gonna put this summation notation, right? Sigma, I got I is equal to 1. That's easy, right? We're just adding stuff up.
Yeah.
Oh, okay, I go to 12 and it's just I. Done, right? Next one, what did you guys get? I is equal to 1?
1 over I squared.
Yeah, this also goes to 12.
1 over I squared.
What
going
if we
to
do
12.
1 over I squared and then we put I equals 0 as the index?
You could, so here's 1, or just to get fancy, I is equal to 0. And what are you trying, where are you going now?
What
Is it the
happens?
same thing?
Well, because you
No, it's
have,
undefined.
yeah, because you have 1 over
0.
0 squared. You just don't do
No
that
fun.
because you don't want to do that to yourself.
Oh, so sometimes you can, sometimes you can't, okay.
Oh.
So not possible, right? How about this one? See if this works. How about if I write it like this? I is equal to 2. We're going to 13. So I minus 1 squared. Will that still work?
Yeah.
Yeah.
Oh, cool. Okay, so these guys are, we call, they're not unique values, right? I can write this formula however I like.
Oh,
So I is equal to 42 and goes to 56.
Absolutely.
1 over
And subtract
42
45.
minus 41 squared.
We good? So yeah, a whole bunch of different options here, right?
Not.
Okay, and then the fun one, of course, the fun one, C value.
Yeah.
I have an X inside there somewhere.
And always being 42 is.
And notice the sign changes, right? You have a 1, then you have a minus. So you have a positive 1, and then a minus, then a plus, then a minus, then a plus, and a minus. The way we get that, we can just take powers of -1. And with this one's kind of cool because at the end, when you see end values, you kind of know what the formula is going to look like. Because I'm giving you the formula.
I like this going forward a lot more.
You can actually figure something out, right?
The powers are, oh, wait, okay. Wait. But then how did it-
What do you go to? Do you just go to the end? You do just go to the end.
Is it?
You guys talk to me. All yours.
is I
Go for it.
equals-
I equals 0.
No. It'll be I equals
Let's start with
1.
I equals 0, because then you have, that's up to the 0 power is gonna equal 1, and then it'll, to the first power it'll equal just
This
x.
is true.
Would it be
Perfect, good.
negative x to the I?
Negative x.
Negative x to the I?
Wait a minute.
Oh, that's cool
Wait,
too.
the
let's
formula's
see.
right there.
Hey, all right. We go to n. And the formula is -1 to the n.
Ooh.
It's -1
Next to
to
the end.
the I.
And you guys talk to me here. Does this also work? Because Kate said this would also work too. Talk to me. Is it just -x to the n? Is that the same thing?
Yes, that is the same thing.
That also work, right?
It wouldn't work on a calculator, but yes.
No.
Why wouldn't it work on a calculator? You just need parentheses.
So yes, both of them work. Again,
Parentheses.
still
We're
not
working on
unique.
parentheses.
You need parentheses in the first one too.
And then let's see, we normally like to isolate the -1 in just in math in general, because that just is that one little piece thing where you can work with the formula, because the formula gets more complicated than you have that little variable by itself. Okay,
I like the ones with.
Next slide.
so now let's go on. Okay, intro, good. Now let's go to special cases. And what I mean by special cases is we can get a specific formula out of it, which will help us. So special cases, there are 5. 5 special cases which we like to have formulas for. First case, boom, sigma I going from 1 to n of just 1. That's fun. My question is, what is the expanded form? But eventually, what's the formula that gets me there faster? Is right. So let's see, let's talk about the formula itself. So really what I'm doing is I'm doing this, right? 1 plus 1 plus 1 plus 1. How many times? N times, right? Just to the n, right? Because n is our stopping point. Or else really, what's 1 plus 1 plus 1 plus 1 plus 1, 1 plus 1, n times?
Is
Infinity.
n
Or
times
is n times 1?
Yeah, or just n, right? Oh, cool. So first little formula. I going from 1 to n of just 1 is going to give us n. So box it in, formula number 1.
We
Love
did, didn't we do this in algebra 2?
Yep, should have done it as a tail end of algebra 2. That should have been the last thing you
this
did.
seems vaguely.
I did this.
Oh no, you guys did
part in
hyperbolas last, right?
Yeah, we did conic sections. after
Conic
we did this.
sections. Uh-huh.
But we got this part cut off because we went to COVID and then, yeah.
Uh-huh.
But I think we might have done that.
Yeah. Okay, second special case. Let's see if you guys figure this one out. It's the same thing. You expend it out, and once you expend it out, you sort of see what it would be here. So how about this? A constant, just a constant by itself. What would be the formula? All yours, and shout it out if you have it.
And
That's cool. Okay, that was like a small shout out, like NC.
Gotta say, objection.
what?
So same thing, right? You have a constant that's been added in n number of times. So formula is NC is good by me. That's cool. So you just really just multiply the index, but you know, actually, no, you multiply your stopping area, right? Times C. Does it get more complicated? Yes, especially if you start at like 12, right? Start at 12, go to n, then you have to do a little bit of work there to get it. But as we're starting with 1, we'll get that one. Box it in. Formula number 2 is all set. You guys tell me if I'm going too fast.
For now, I'm not going to finish.
Okay, next one. Let the fun begin. Okay, cases. How about this guy? This is fun. I really get a kick out of teaching this little section right here. We did it, we did it, we just didn't do a formula. We calculated it, but not to the nth
Come
value.
up with a way to do this quickly?
Say again?
Didn't Gauss come up with a way? to do this
Frederick
quickly?
Gauss, sitting, I think, in like 5th grade or
Yeah.
I
something.
feel like
The
it's
teacher
first
told him
grade.
to add up all the numbers to like 500
100.
or like a ridiculous number, and he's like, okay, here you go.
We did it in, like,
Yeah.
2 seconds.
Let's do the process. Yeah, from 1 to 100, right?
Yeah.
And so let's go to, let's see how this works here. So 1 plus 2 plus 3 plus 4, right? Eventually it goes all the way out to n minus 1. Let me add an extra little piece in there, n. So Frederick Gauss, he was required by the teacher to multiply from 1 to 100. And he had this little understanding. If I'm doing this, kind of cool. 99 plus 100. He goes, okay, I need to do this right here. So then the question is, hold on, if I were to just say this is n, or x in this case, and I were to flip it around, because really you get the same thing, don't you? 100, 99, 98, all the way out, you're going to eventually get 2 plus 1. That's cool. So hold on, what happens here? I get 2x, right? But I get 101 plus 101 plus 101. How many times?
'Cause you can divide by 2.
Yeah, so again, in this case right here, that's 100 times, right? So Gauss was saying, okay, if that's true, then hold on, this is just 101 times 100. And then Eli says it's 50, yeah, because we divide by 2. So then it becomes 101 times 50. That's cool, we good? Okay, let's do the same thing here. We'll keep all this. Erase, just kidding, erase everything. So I'm gonna write another one. Aw. I'm gonna write the same exact one right over here, except I'm gonna go backwards. I'm gonna say, okay, if that's true, this is n minus 1, and we go all the way back, all the way to back to 1. We good? Still same thing, right? I just kind of wrote it backwards.
Is this still 3?
Yeah, this is still case 3. We're making it. And if I were to add this up, I'd get 2 of these guys. And I got myself n plus 1, and another n plus 1. And I got this how many times again?
N times.
N times. That's cool. This happens n times. So divide by 2, or maybe make it into a multiplier here.
Is that 4 or is that still?
So it's n plus 1 times n divided by 2.
That'll work, Cool. Okay, guys, again, tell me to slow down if I'm going too fast. So that means there's 2 of these guys. Let's see if this makes sense, which would equal n and n plus 1, right? If I'm trying to solve for one of them only, I got myself index going from 1 to n of I is just n plus 1 divided by 2. Now we can box that in. There's my rule 3. Super cool, super cool. A little bit of work there. It's fascinating, the fact that we can sort of think through something and advance a field just by thinking through something.
Trader came up with that. That's insane. Genius.
There was a quote here that we were talking as a family here, like ideas become things, right? So you postulate something and like, hey, how about if this, and eventually that actually materializes in something, right? And so I thought that's kind of cool. Okay, the other 2 formulas that we have, let me just check here. I think it's, I'm gonna, this formula here. So we have I squared now, and I'm gonna give you the, I'm gonna give you the formula to it. We good? It is a little bit too lengthy of a,
Sometimes there is.
let's see if it's in
Casey
your book.
handwriting is perfect.
Okay.
His handwriting is tiny.
It's not tiny.
It's not tiny, it's just right. My handwriting is a monster.
This was my
Oh,
midterm.
pretty. Oh, big. Oh, it's so pretty. My midterm was so messy.
She also said I should have expanded more, so with that.
Okay, last two formulas, I'm gonna give them to you.
What?
And
Give
they,
it to
I
us?
know, yeah, so if you want to do a presentation on them,
Oh, okay.
at the end, there's some presentation
Oh, no, what would you do
possibilities.
for a presentation?
Don't worry about it after.
There you go. Or you could look at Appendix E in your textbook, one of the
I'm
two.
trying to think of something exciting to bring.
Oh, these are like.
Me too.
I was totally what I was gonna do.
So there it is. Can you prove those formulas for us? But we'll need them later on, especially this top one. In fact, we'll work with the top one today because we'll be looking at x squared. So all yours to copy those down, and let's go. Box them in if you like, just to make
Next
sure we have them.
slide.
No, I'm still writing that.
Hurry and write it down so we can.
Write down faster.
You're still writing it down, Sadie.
I'm not. I already wrote it down.
Yeah. How come you're so slow?
Come on, Christopher.
What color pen is that?
It's a pumpkin.
Why are you writing? Does it have like, is it one, the one that kind of makes ink in all of your hands? Old soul. Wait, is that the type of pen writes this?
Yeah.
Yeah.
I think I would get it on because the way that I write single-handed, it would smear off.
Oh.
Well, yeah, you're left handed.
Yeah, that, it stays wet, right?
I mean, you want to try it?
No, it's fine. We should go to the next slide.
Next slide. Okay, so let's practice here with it here. So now we know how to do this stuff here. Let's find the value of this guy.
Oh, like you know how much lead you broken.
But I am not out of line yet.
I breathe
Hold on,
so
sorry,
much
sorry.
blood when I use my pen.
Boom. Sorry, that should be N. Sorry, guys. That's really for Christopher using a pen.
Luckily, I didn't write it down.
No, you almost got it.
I'm just waiting. I ordered 2 giant, like,
Oh, just to make it, guys, just to make it a little easier and waiting for Christopher to write it down, let's go to 1, from 1 to N.
Oh, you didn't have
excuse me.
Hold on, does Sadie have a pen too?
Yeah.
Yes, I
Got him.
tortured somebody
Yeah.
to make it easier
You
here.
gotta convert them, Mr. Hunt.
You could start with 3, you could start with 12, and what happens is you gotta subtract the beginning part out. You still go from 1 to N,
Mhm.
and then what you do for this one particularly, you're gonna subtract out 1 to 2. And that's how you get the little value there. Yeah, sure. So see how we're going from 1 to N?
Right.
If the same problem was like this, it was, let's say we started at 12, right? So then what you do is you say, okay, I'm going to start out with 1 to 11. Sorry, 1 second. I'm gonna start off 1 to N, but I'm gonna subtract out the beginning part of it. So I'm gonna subtract out from 1 to 11, we good? And that'd be a value. No, talk to me if that went crazy.
Oh, I remember I get it.
It's in, we good or no? You guys
Wait,
talk.
why do you want us to do
You
this
like-
again?
No, okay,
No,
let's forget that.
What? I think that was just like.
It's
a
if we
way-
didn't start at 1, then we'd have to subtract out the part that we're not gonna use, we still wanna do it from 1 to N.
Yeah.
But here we
Eventually-
just took it and changed it to 1, so it's easier. You know?
Sorry, Christopher, just to destroy you a little bit here.
Alright, cool, yeah, I remember
Okay.
why I struggled in algebra 2.
So 1 to N, that's what we want to do. Okay, let's go for it. So if I'm going to do this here, I'm going to do this.
I didn't find it.
I to that, and this now becomes I squared minus 2I. Are we good?
Yeah.
We're good there so far? Okay. So then I'm going to do this. Distribute this sigma absolute to each piece
Wait,
here.
what?
So
You can do that?
I
What?
squared.
What?
And-
my
Becomes
God.
much easier.
2i.
Yo, that's so cool.
It's the same thing in geometry. You guys remember from geometry when you're looking at areas of stuff, this like
Yeah,
here,
like
and you
it
say, okay,
is.
find the shaded region, right? And this is circles actually meeting the middle, right? It says find the shaded region.
Oh, I hated those.
Remember that?
problems.
You take the,
Oh, that's.
Those
Oh.
are fun.
you take the whole entire box, right, and
They
subtract
told
out
you.
the stuff you don't want. So
No,
same
My
thing
mom
here.
would get along so well. She loves this problem.
I don't like actually like doing the multiple, like long division or multiplication. I like figuring out the missing.
So you guys talk to me. What should we do?
Well, the I squared.
Yeah, I squared is
Blah, 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 blah.
N.
Just n plus one,
n plus 1
2 n plus 1.
over 6, perfect, minus, and then that little 2 is gonna be a multiplier anyways,
But why
right?
is it over 6? Do we switch it
From,
back
from
to
the
six?
formula, that you're gonna prove for us.
Because the
formula's
formula said
always
so.
Yeah, formula's always 6 for these. So the 2 is a multiplier to I.
I don't know if I trust that one.
So you
And-
move it outside of the sigma?
I would move outside of sigma as long as it's a multiplier.
Two.
So if you multiply 2 to every single problem, or you factor out the 2, it doesn't matter.
Wait, it's just -2.
And
No,
it
no,
becomes
I, what is I?
Which makes it equal
And-
to 2,
Wait,
n plus n over 1.
Yeah, that's gonna be an n. So 2 times n plus 1 n over 2. Wait, the 2's gonna cancel itself out.
Yeah.
Okay, and then we gotta simplify, so the simplification begins.
Oh no, back to
Oh,
algebra.
boy, yes.
It all
So
comes
2's
back.
cancel, that's correct.
We have to multiply.
Except we actually have to put in,
You can't just
We need to
Uh-uh.
multiply the second fraction. by
we gotta multiply this whole thing out. In fact, for the second one, we actually have to put a multiplier of 6 in there, right?
Yeah.
To get common denominators here, so
That's
6
Oh,
over
boy.
6.
6 here, 6 here. As the 6 comes in, this would be what, 6 times n, so 6n squared plus 6n. Are you guys okay with that one?
Why are we?
Yeah.
Because we're gonna have to simplify, we're gonna have to subtract here.
Then you have n squared
All this multiplied together, what is that?
plus n.
2n squared, 2n, 3n,
N plus 1 all times.
plus 1, all times n.
2n,
2n
plus
cubed.
3n, so it was-
Yup.
Almost there, guys.
Then you just subtract.
Uh-huh.
So 3 minus 6.
Oh, we have to keep the parentheses though, so because we're subtracting. Oh, you,
Gets you negative.
I make them
3.
into one
So
fraction.
2n cubed minus 3n squared minus 5n
That sounds good by me. Uh-huh.
over
Bam.
6.
Uh-huh. That's so cool though, but we have an equation. We have we call this an explicit equation, right? We just plug in whatever n is. If we want n to be 100, we just plug in for n and we're done. We don't have to calculate each and every single piece of it out. Super cool stuff.
for that y is 6.
I know if it tortures you, you gotta present it.
I want it to be presented to me. Okay, I think that needs to be your project.
Mhm.
Just convince Kate and Christopher
Convince
to
me
take
that
the
that
two
whatever-
formulas.
The formula, yeah.
Porque?
maybe.
What does
Oh,
core K
it
mean?
means
That's-
why.
Why? It's n.
Well, why would you ever speak Spanish? How's that?
With this southern accent.
Southern.
Southern accent. Okay, we're good, guys. That was the prerequisite stuff we need to know. Now let's jump
Next
into
slide.
the next
For
slide.
a second, I thought you were gonna say.
We're done.
Oh, that's it, that was 5.1,
You thought.
guys.
Oh,
There's no
that
way
was-
it's that. It's even an area.
That was just the stuff we were supposed to remember for algebra too.
That's the stuff.
Didn't Aristotle divide these into like really, really small triangles?
Aristotle like.
Archimedes.
Or no, Archimedes, right?
What he did is he started talking about limits, but he did it more in terms of limits as opposed to addition of things.
He was so, oh, I wish that Archimedes
brilliant.
had discovered calculus.
I know,
He was
that's so cool.
nice.
You'd probably be so much.
The world.
We would
of
be,
Archimedes
we would have
had
exploded the
discovered
world by now.
Mhm.
We would
We would be
in
on Mars.
space.
We would be on
Let's be honest.
We probably would be dead.
Yeah.
What?
Why would we be
Why
dead?
would we be dead?
Because humans are.
Yeah, humans would have killed themselves.
Yeah,
But then we wouldn't have to suffer through.
we're very smart, but we're also very.
We wouldn't have to suffer through the death.
Okay.
Okay, as we do
I
that.
mean, would you
We're
rather
jamming.
be dead?
Come on, next
than
slide.
never existed,
So what are we
or-
trying to do in calculus? Here it is, right there. We're trying to do that. We're trying to figure out the area underneath the curve.
You can imagine though.
Let's see, and once we figure that out, a whole new world opens up to us. Let me just give you a little preview here, because if you think about, this has to have some imagination here. If you were to rotate this guy around the x-axis, do you get a solid figure along the x-axis?
Yeah,
It's kind of like almost like a bell shape, right?
yeah.
Solid bell shape. So if I can formulate it like a Coke bottle on top, and I could rotate it, could I get the volume of the Coke in the Coke bottle?
Wait, but we don't do 3D objects.
What do we, area, not volume.
Yeah, so by spinning it, I can get volume.
But we're not,
If you
like, if you spin it,
The chapter of
spin it
this.
like 360 degrees around the
You
x-axis.
just keep
Uh-huh.
rotating it?
Just keep rotating it.
Oh, you're talking about that? Oh, yeah, that is so
Oh, wow.
cool.
So not only not only do we get area, but spinning it, we get volume. And then also, could I rotate it along the y-axis?
But do we do that during
Ah.
calculus 1?
Absolutely.
Okay.
But then that would be like a donut if you're rotating around the y-axis.
That
It's
is
a
so
donut with a
cool.
very
Would there be a
strange-
hole in the middle?
Yeah, we get a hole in the
There
middle.
would be a hole in
And
the
then
middle.
it would be weird shape.
Then we could
Uh-huh.
turn it into a coffee cup with
It would be like a
topography.
Uh-huh.
No.
And we call it actually the washer method, because whenever you guys use washers, right? Don't we have that kind of shape, right? If you put washers when you do stuff. So washers means we have holes in the middle, and we only want the area on the outside or in between there. So we can form any, in a sense, any object we want.
Any
Topography.
objects?
Ooh, any
Rotating it
object.
makes it
Really?
easier to
What
find
about?
that area?
Say again?
Does rotating it make it easier to find?
Yeah, what does
Or what
rotating
is-
it do?
Yeah,
Well, if you
rotating it takes it into 3 dimensions.
Yeah,
You get a
that's
3-dimensional
weird.
object.
Why would we need to take it that into 3 dimensions?
Because we wanted other things that we
I thought
don't
we were just trying to
necessarily.
find
If you're
area.
ever stuck
Uh-huh.
in a 2-dimensional Cartesian plane, you just have to rotate it and you'll be transported.
Just the one that's spinning.
Right.
If
So-
you wanted to
Sorry,
make
Sadie.
a
Okay,
smart-
Good. Okay, let's jam. So here's what we usually start off with, and thinking about this here. So example 1. Oh, what example are we on now? 3?
we're on example-
4. This is example 4.
Really? Oh, yeah, 4, this is example
4. Okay, example 4. And this is usually the example most calculus books use just to show this here. So I want to find the area underneath the curve of x squared. I'm going to go from 0 to 1. And so the question is, how do we do this? Once again?
Let's go back to the sigmas.
Yep, I'm sure it's going to come together somewhere. So I'm going to draw it. Let's see. I'm going to draw this like this right here. And this would stumped us for a lot of years, from Archimedes to, but finally we figured it out. It took 1,500 years.
Come on, that
Right
was
there.
a long time.
When did they figure it out?
No, 1,700 years, almost 1,800 years. So we had to get Leibniz notation for derivatives. Once we figured that out, then we needed, because it's all about limits. That's when you had to have a really understanding of limits and like, oh, that's right. So let's see how limits kind of play into here. And it's not going to be the limits that we did in chapter 2. It's not going to be all these rules and stuff like that. It's actually much, much simpler. And once you see it in calculus, it's so interesting. Once you see something like, that's so simple to do, right? But it's just being the first one to do it. That's the problem.
Yeah, that's what I think when I look at calculus. That's
So-
so simple, I could do this.
Let's see, we're going to get you there, Christopher.
Do that
So
time.
question is, how do you get area here? And so we've thought about, you know what? How about if we just break this up into pieces? So if I do this, if I go break this up, let's just say 4 pieces, here, here, and here. And what I'm going to do is I'm going to figure out the point here, and I'm going to make a triangle. I'm going to get the area right inside here. And I'm gonna go up to the next one. I'm gonna go up here. And I'm gonna get the area here. And I'm gonna go up here again, get the area here, and then I'm missing one piece. I'm missing the whole piece, so I'm gonna all the way up to 1.
Oh, then
And
it
I'm
can
gonna
make. Let's go back to limits though, do infinite rectangles and you would get the.
Absolutely. So now the question is this: if I get more and more rectangles in here, will I get a more precise view of it?
Yeah.
Yes. If I can go all the way, do I clear my air in the process? That's my question. And so let's go with it here. That's the adventure we're going to be on for the next 15 minutes. So I'm going to say R and I'm going to say 4. That's going to be our notation. R means I'm going to take the right-hand side of my values and I'm going to use that as my.
It's resistor 4.
So my question, let's see, this is 1/4, right? This is what, 1/2? And this is 3/4. So cool. So I guess my question is, what's my length of each rectangle? A quarter, right? So I got a length of a quarter. And then I'm going to have to put my value, which is 1/4. I'm going to square. Why am I squaring? Why am I squaring? Let me give you a clue. Right, I'm trying to get my height, right? To get my height, I just need to figure out my function. Yeah, plug an X into my function. So I got that guy plus, again, my length of my second triangle and my height of my second triangle. Width of my third, rectangle, sorry. And I can't say length and width anymore, huh? Because now that actually has turned into a width. Width of 1/4 and a height of that value there.
That's million to do all of that.
Yes, Okay, just because we're pressed for time, I'm going to do this here. It is exactly 1530 seconds, which is approximately 0.46875. Are we good?
Okay, yep.
Now, notice that we're actually overcompensating, right? So that means we know that this guy is less than 0.46875, right?
Oh, because,
Yeah.
with the extra area above.
Because we,
Is there gonna be a point where we have
eventually.
to take out the tops? I don't
Wait,
think
so what if you
Yeah, good. All
did
yours.
another set of rectangles beneath it? And then you would find the air, then you do the actual area would be like.
Yeah, and that's
See, you can, Enrique. You can't
absolutely.
cut off the top.
Eli's onto something very important here. So how about if you go underneath it? The only problem is, yeah, you're going to extend from here, though, right?
Yeah.
So then you have to extend from here, and we have to have a point which we are going to do this, also a point which fits a pattern, right? So we have to have that pattern in place. And so let me jump, just one more question, one more idea beforehand. So notice it's not always going to be this way. If I have something goes like this, notice the air is a lot less, right? Because I have points that go above and points that go below, right? And so to answer Eli's question, though,
Wait,
yes.
did we do this before?
No.
We did this, we looked at something like that maybe.
First or second day of class, I just kind of showed you
Yeah, you
about
showed us
this.
that.
Look at this.
And said, yes, we're gonna do this in like a year. And then half the class was like, I'm not gonna be here in a year.
Okay, don't write this down because I'm going to kind of quickly. But to answer Eli's question, yes, let's go for it here. What we're going to do is we're going to do this and we're going to label it as what? Okay, what? How about 1/4? How about 1/2? How about 3/4? And Eli says, let's get under. Can we get under somewhere? Yes, we're going to have to do this. Does that make it under? And notice what we're doing. Are we taking the right-hand side of these things? We're taking the left-hand side, so it's left 4. And notice what happens here, though. This is, we still have a gap of 1/4, right? Kind of think with me as we do this here. What's my first point? If I'm taking the left points now, what's my first point? One's over here. So let's see, go back to my previous slide. Yep. So this one we took, that was my first point, second, third, and fourth, right? Notice I'm taking the right-hand side of each of my rectangles. Here.
The left-hand side.
I'm taking left-hand side, 1, 2, 3, 4, so 0. Then I have 1/4 times 1/4 squared. Are we good there? Okay.
And then you take the average of these two, that will get you.
Oh, maybe yeah, we could take the average of them. That would work. Let's see, that still won't get them. Okay. 7:30 seconds. Approximately 0.21875. Are we good? Cool. And so the whole point of, again, this is pre-calculus, pre-calculator, right? Because we don't have a calculator, we can just run the numbers, right? But so now the question is, how do you fill this gap in? In fact, let me show you one more. The other way to solve this error was to do something called the midpoint, right? You have the left side, you got the right side. We can also do this one right here, which might mitigate for us. In fact, this was the popular one for a while. So let me just show it to you real quick here. There it is. How about we just take the midpoints of that, midpoints of that, midpoints of that one, and that one. Are we good? The values? What are the values here? Let's see if we can get the values. M4.
They're just a lot more.
1/8. Perfect. Yeah, 1/8. Again, notice we can get a pattern here. Yes, as long as you can get the pattern. 5/8 and perfect. Okay. So again, don't write this down because this just be fast. We're just kind of concentrating on the concept here. Cool. So this guy gets me 21/64, or approximately that right there. Cool. Again, yeah, we're stuck with all these. So which one do I use? And then how do I form it? And so now that we're in the age of calculators, if I start setting up a pattern like this, and I start putting these closer and closer together, in fact, especially the right and the left, because those are my two extremes, right? And notice what happens here. Just kind of quickly look at this. This is kind of cool. If we use 10 divisions, we get these two numbers. If we use 20, 30, 40, 50, 100, 1,000, notice which number are we sort of getting closer to?
Is this the golden ratio?
No, not the golden
Not the
ratio.
golden ratio, but the one that's used in it. Oh god. I can't remember. Wait, is E the golden ratio? No. But that's not E. E is like 2 points.
With 3, it's 1/3.
Okay, I'm gonna go with, I think there's a whole bunch of 3s that are being set up here, right?
Oh, yeah.
I'm thinking maybe it might go to a 0.3333 eventually. Let's prove it. Okay, now let's get abstract, put your thinking caps on, let's jam. So same exact concept, same exact graph, except this time, we're gonna think about this. We're gonna try to divide this out. We're gonna do right hand. We could use left hand too, that's fine. We're gonna use the right hand points, and we're gonna do a whole bunch of them. In fact, we're gonna use n of them. We good? And let's see what we get. Let's see if we can put this together. So we're using the right hand, so this is R of n. So question, we divided this into 4 pieces last time, right? And this is the one you want to write down. Let's write down with this one. And tell me if you need to slow down as well. So we used 4 pieces last time, and the width of each one was 1/4. We good? We're going to divide it into n units. 1/n. Okay. Perfect. And we're going to go from A to B, right? A is the starting point, B is our ending point. Okay, using our right-hand side, again, this is super fast-paced, thinking through ideas that took 40 or 50 or 60 years to formulate, right? We're going to do it in 5 minutes. Because we're cool like that.
Awesome.
Okay, next piece is this. Let's think about this here. What happens for the values? So notice, go back to what we did on the right-hand ones. What did we start off with? What was our first one? 1/4, right? Because you're taking the right-hand side, the first one is going to be the first width that you get, right? And our formula is squared. So this is only going to work for a squared formula. Okay, then we do this one. We take another nth slice. And what do we get for the, when we did 1/4? Yeah, 1/2, but isn't that really just 2/4? So really you get, so let's go one more here. So if I'm at the third one, for a third one, we got 3/4, right?
Yeah.
So that's just 3n. So we slice these out, and then you can keep on going forever until 1/n. And eventually get n/n squared, right? That's going to be our last one. And that's exactly what we got on that one. Didn't we use 1 eventually?
Right.
Cool, I like this. Okay, next thing's next. Let's see, let's make this into a formula. How about 1/n is that first one? I'm gonna just factor stuff out. Can I factor 1/n out of all these guys?
Yeah.
Cool. What else can we factor?
The square.
So these guys are gonna become 1/n squared. That'll be 4/n squared, then be 9/n squared. Can I factor the n squared on the bottom?
Yeah.
So I'm going to factor out a 1/n squared out of each of those. Everybody okay with that? That's probably the most complicated thing that we do there, right there. Everybody okay with that one?
Yeah.
Okay. So what am I left over with? I'm left with 1 squared, is that right? 2 squared? 3 squared? Hey, I noticed this little guy here. I'm going to go all the way to n squared. Can you help me out? Do we have a little formula that takes summations of square units from 1 to n? I think that's the 1/6 thing I'm going to give you, yeah. Perfect. Okay, so real quick here, I'm going to multiply this together. This will be 1/n, and 1/n squared makes 1/n third. So 1/n cubed. And the formula says n plus 1, 2n plus 1/6. Awesome. Can we simplify this at least a little bit? Yeah, n's cancel. That little n in front right there. And that will n will make n squared. Okay, so I got myself n plus 1 only, 2n plus 1. And now on the bottom I have n squared. Sweet. That, I don't know if that helped me, but we'll see. Okay, so now I have an explicit formula. This is the interesting thing, is that's why limits were so needed and these formulas were so needed to figure out. Now I have an explicit formula. And Gauss, being in 5th grade, when he did that, that was amazing because it opened up this whole new world right here. I have an explicit formula for summation. Now, if I have an explicit formula, the question is, can I just take the limit as n goes to forever? In fact, you guys did this in algebra 2. It was called the horizontal asymptote. Remember that? You're trying to figure out horizontal asymptotes of the x going to infinity. And what we did there is, let's multiply this top out. Let's see, n plus 1 times n, 2n plus 1. That would make squared plus 3n plus 1. Okay, on the bottom I have 6n squared. Okay, guys, talk to me. And we actually did limits like this anyways. But what happens if you have the same exponent on top, exponent on the bottom, and you're taking the same degree exponents, and you're taking n to infinity? How do we do that in algebra 2? How do we get rid of them? Yeah, we can cancel them. So like the proper way of doing it, what we do is we just divide out by the highest exponent. So divide out both by the highest exponent. And we get ourselves, let's see, the big, if you want to write this one down, you can, but it becomes this right here, right? You're dividing each of those pieces by n squared. Almost done.
That could be simplified.
That can, absolutely. It looks complicated, but really you're talking through the pieces here. So quick question. N squared over n squared is not just me one? This 3n over n squared, what happens here? 3 over n, and then n's gonna go into infinity. 3 is gonna get really small, in fact, goes to 0, is that right? So the only thing that remains off of this, yeah, I should write it in. So let's go with it here. Limit as n goes to infinity is going to be 2 plus 3 over n plus 1 over n squared. Nothing canceled there, over 6.
You don't care about the 6.
Let's see, that guy's going to go to 0, right? That guy's going to go to 0 because you have a fraction. Absolutely, everything goes to 0 except for the 2 and the 6, and we got ourselves, and Eli was correct. How about a 1/3? So now the question becomes, does that get rid of all the air? Is it exactly 1/3? I know the numbers went to it, right? Okay, so if I go from the left-hand side, will I get the same thing? And sure enough, I'm not going to write it down, don't want to do it, but if you did the left-hand side, let me give you the slides to it here. Okay, and then we got to do the general function here in just a bit here. Okay. First of all, real cool or not cool? I think super cool. Okay, so we have finally, I think we have finally got the area underneath x squared. And so if we do it from the left-hand side, it looks like this. Don't need to write it down, just kind of think with me as we do it. I chop it up into n pieces, is that right? This one's it gets a little more complicated because from the left, we start off with 0. And instead of going to n, what we do is we actually go to n minus 1 on this one. And that, it's way easier to go from the right side just because it ends exactly where n is each time. So you have this sort of like n values. And so your sigma notation goes from 1 to n. Easy. In this case, that goes away. That's nothing, except we have to compensate for the fact that we are not going to n, we're going to n minus 1. And we stop there. Okay, how do we compensate? Again, this is the formula to go to n. And again, you won't have to do this later, so we don't have to do it right now. If you only go into n minus 1, the formula then becomes, just substitute n minus 1 for each one of those.
Is in.
So n minus 1 goes in for that one. N minus 1 plus 1 is just n. And
minus 1.
simplifying that version out, you get something that looks like this, right? So you're going to plug in that formula. So as you plug in that formula, and simplifying it out further so it's not as nice or nicer looking. And voila, how about this? Plugging in this formula, simplifying as much as we can. The n cancels in the front. And notice it's kind of beginning to look like the same thing again. You got minuses instead of pluses. Yeah, but who cares? Because what happens, we only care about what's happening in front, right? Because everything else is going to go to zeros. So that minus 3 instead of a plus 3 is there. And you got a minus 1 over n. But any which way, who cares? Eventually, you get to that. And how crazy is that? Why is 1/3 so important? Remember in the beginning on the right-hand side, we were overvaluing our case, right? On the left-hand side, we knew we were undervaluing our case. So what happens when those two converge in the same exact property and the same exact number? Awesome,
I wonder
right?
now for find the area of like a function going into the one, one over the plus one, probably not. No, probably not.
Oh, no.
That's under x squared is 1/3.
1/3 from 0 to 1, right? Because we have a
Yeah.
beginning point and end point. As soon as you go higher than that, you gotta, oh, hold on. If you go higher than that, you gotta redo this whole process all over again. I wonder if there's a simpler way.
I wonder.
But let's do this here. First, we gotta go to the general function. Okay, thinking caps on for a little bit here. General function. I have this right here. I'm going to break it up into a whole bunch of different units. Forget the stuff that's on the bottom in light blue. So we like using the right-hand side. We could use the left-hand side. We could use the midpoint. It doesn't matter. But we're going to stick with the right-hand side most of the time.
This is x1, x2, x.
And then xi. Xi is important because that's going to be our.
X and minus one.
Then this n minus 1. And then you know the last one right over here is going to be x sub n, right? The b value becomes x sub n.
B, okay, B equals x again.
Okay, guys, we do have 3 minutes to do it here. I'm going to try to put this together. I think we're going to be missing one more example. And then can I send that to you guys via a video? Because I think we got through the crux of it here. So let's put this together in the last few minutes. First things first is I'm going to call this guy here from here to here. I'm going to call it delta x. And see if you guys agree. Delta x, the way I find what delta x is I take b minus a and divide it by n. Does that make sense there? Okay. As long as we're agreed or disagreed on that one. So I take the range, right, b minus a, and then divide it by n, and that's going to give me my width of each individual piece. Cool. Next, when I start doing this here, I go x sub 1 is really a, my starting point, plus delta x. Agree there.
I think. No, I think I'm starting this, like, I think I know where it's going to go.
So if I go delta, now I'm going to try to get to this point right here, right? So my starting point is here, and all I really need to do is I need to go 2 delta x's, right? I need to go to the second one. So how about just 2 of these guys? Are we good there? And eventually we're going to do n of these, right? Yeah, but in the middle, we have this right here. So any kind of like, any slice in the pie is going to give me xi, and it's going to be a plus I delta x. And that's important because that's going to give me to my index for summations. And eventually I end up with x sub n of a plus n.
Does that say x of 8 or x of n b? Well, are they both n?
N and n, Now, those indexes are the same.
Wait, are you looking at the one that's boxed?
Yeah.
The one that's boxed is I. The one below is N.
Thank you. Okay, so let's see if we can put this. So hold on, oh, that's so cool. So if I make these into functions, are we good? If I make these into functions, that's going to be my height for each one of those. We're good? So if I say this right here, I'm going to say f of x sub 1, f of x sub 2, and in the f of x sub I is going to give me the height at any place along my curve. Are we good? So let me give you the definition and we're done. I could do the left side. I could do the midpoint. In fact, I could do any point in here whatsoever, but let's do the definition. The area underneath the curve of a generic function, and we'll stop here because Ms. Baird needs to start class 2 here, is this right here. It's the limit as n goes to infinity of the summations of okay. Okay, see if that makes logical sense.
Okay.
With 20 seconds to go, can you guys write this in summation form? In fact, we should say this: area underneath a curve of any function whatsoever. Is that right there? Now this is just using right endpoints, so we should actually say right endpoints. Okay, and then writing it the condensed form. How about this? A is equal to the limit as n goes to infinity of the summation starting at 1 going to n of the height and the width of each of those rectangles. Okay, I got 2 examples that I haven't done yet. I'm gonna do a quick video today, send them to you because that's been part of the homework.
I have a quick question. For the previous problem, why didn't we have
Let's say XTN.
like the
XD.
1/4 squared, 1/2 squared?
X sub I.
Yeah.
There's no not
Not.
Sure, let me talk to you after I finish class, so Ms.
Okay.
Barrett can come in. Okay, are we good?
Yep.
So I'm gonna give video, I'm gonna send you guys a video of 2 more problems, which are gonna be kind of like the homework here. As far as homework is concerned, let me write this down. You guys have 5.1, you guys are gonna do 1A, 17 and 21. Then you're gonna go to the back of your textbook, and you guys are gonna do appendix E. Okay, please tell me, they're just writing down their homework assignment.
Wait, so,
Sorry.
so only 1A, 17, 21 in the appendix?
Appendix E, that's the summation stuff that we did in the beginning. Those are the prerequisite skills to get your 5.1. Absolutely. What do you guys say? Was that pretty cool?
Yeah. Very cool.
We did 60 years of math.
Whoa. Thank you.
All yours. Thank you so much.